Welcome to this video on differential equations. Differential equations are a very important topic in mathematics because there is a huge category of problems that you can describe using them. And actually, studying differential equations and how to solve them, both using pen and paper, analytical solutions and numerical solutions, is a large category in mathematics that many people work on. So in this presentation, I'll touch upon differential equations. I'll give you some fun examples of things that you can model using differential equations, and we will study one way to solve differential equations using what we know from integration. So differential equations are equations where the solution is not a number, like you would have x squared minus 7x plus 6 equals 0 when you would find some values for x, but they are equations for a function. So the solution of a differential equation is a function. Now, let's have a quick look of what we will see in this presentation. So I will tell you first a couple of problems that you can model using differential equations. I will give simpler problems that we can actually solve using pen and paper, so we can find what are called analytical solutions for them. And then after we have seen a couple of examples, I will sketch the category of differential equations that we are able to solve, which are called separable differential equations. And I finish this video with discussing the population growth model. So think of the number of people that live in a country and how that number depends on time. So let's first look at an example. So one of the most successful or famous examples with differential equations is planetary motion. So Newton's law of gravitation that you already know from high school. And in fact, there is a paper by Eugene Wigner, and this paper is called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And what is basically discussed in that paper is that if you find a mathematical description of things in nature, that very often they are very concise, very compact. So it's like one equation that describes something, and then it's ridiculously accurate. So it is only an approximation of what is really going on in nature, in daily life, but then it makes predictions or it explains other phenomena with incredible accuracy. And one of those examples is Newton's law of gravitation. So Newton did a couple of experiments with falling bodies, and he found that if you have two bodies with certain masses m1 and m2, that they have a force on each other, and these forces f1 and f2, the size of these forces, of course they are vectors, is given by this relation. So it's some constant, the gravitation context, capital G, and then the product of the masses m1 times m2, and then you have to divide by the distance between them squared. Now, if you have this model, so based on very few observations, it is extremely accurate. So as it says here, a 10,000th of a percent, so extremely accurate. And what is also interesting is that it works for things on Earth, but it can also explain how planets move in a solar system. So this is accurate beyond all reasonable expectations. So that's why it's called the unreasonable effectiveness. And this is just one example there. Now I want to discuss this a little bit further, and the equations on the next slide are going to be way too difficult for this course, but I just want to show you that with a couple of equations we can explain how the planets in our solar system move, which is almost incredible, I would say. So if you look at the solar system, and then we look at the sun, and we consider 5 planets, so Jupiter, Saturn, Uranus, Neptune and Pluto. And here are the orbits. So we fix the sun is in the center here. So the size of these black circles, that doesn't indicate the size of the planet, it's just the location. And the way that you would describe this mathematically is using vectors. So we have the masses of each of the planets, and then we have the position in space. So Qi is a 3 vector with an x, y and z component that explains where the planet is at a certain moment in time. T is time. And then pi is momentum, and momentum, as you may recall from physics, is m times v, so the mass times the velocity. Now, as I said, the equations are way too complicated, but I just want to show you that you can introduce a quantity, capital H, which you can compute using the Q's and the P's for our 5 planets. And then the movement, so the complete movement in time, is described by these differential equations. So we have that the time derivative of the position is apparently 1 over m times the p vectors. And the time derivative of pi, so the momentum, is, well, this is if you would differentiate h with respect to qi. So this is too difficult and you don't have to really understand this here. But I just want to show you that planetary movement is described by these 10, because we have 5 q's and we have 5 p's, vector equations. And these are called differential equations. Now, as you can probably understand, they are way too difficult to solve analytically. We cannot find any pen and paper solutions here, so you would have to use numerical techniques. That is a whole different area of mathematics. If you're interested, we have courses on them at Eindhoven University. But here I used 3 different, rather simple numerical methods to solve differential equations. And as you can see, there is also a lot of work there, because if you use the wrong method, for instance here Euler forward, then what happens is that the planets will not have a periodic orbit, but the periodic spirals out, so that the planets move further and further away from the sun. Of course, that's not physical, you don't want that. Also, the Euler backward method, which is a different simple numerical method, it also spirals, but it spirals towards the sun. So if you use this numerical method, the orbits for the planets that you would find means that they crash in the sun eventually. And then finally, the midpoint rule, that's one of the simplest numerical methods that preserves the distance to the sun. So you get periodic orbits here. Now, we won't be discussing these types of problems here, but I just want to show you this as an application of differential equations. Now, before we are actually going to try and solve differential equations, I would like to show you one more example, which is the pendulum. So a pendulum, as you may know, let me go to the correct slide. A pendulum is just some mass hanging from a rod or from a rope or whatever, and you move it and then it starts swinging like this. You can also describe this with a differential equation. So if we call y of t the angle of the pendulum with the vertical axis, so we have the vertical axis and then we have the pendulum that's in a certain position like this, and then the angle between these two, I call that y of t, so in radians. And then you can show that apparently the second derivative of this angle plus g over L times the sine of the angle equals 0. And g over L, well, that's the acceleration due to gravity divided by the length of the pendulum. So if you take pendulums of different lengths, then they're going to swing in a different way. And I'm going to start the video here on the left. And this is something that I found on Twitter, actually around Easter time, and there was some cheesy music here, an acoustic version of the Stairway to Heaven, but that's not important here. But what you see is because all these rods have different lengths, they're going to move with a different velocity, and they come out of phase and then they go back to the phase and so on. So you get this very nice colorful illustration, and you can probably guess why this was posted around Easter on Twitter. The thing is, if you have the mathematical description, so the differential equation that is below the video here, then what you can do is write a numerical solver for that. And I did that, and once you have that solver, you can take as many of these balls as you would like. So you can take 5 of these pendulums, or you can take 100 if you like. So I did that, and I also wrote a numerical routine to do that. And here I just chose a couple of lengths, and I did a similar simulation. So you should see something there, just a mathematical simulation, a numerical simulation of the same phenomenon. So let me start that. And then you see that here I chose a certain viewing angle. You see that they're kind of similar. Of course, I didn't really know the data from the video, so I just made a short simulation here. But this is something that you can describe using differential equations. So let's leave it at this for now. And these two illustrations, so planetary motion, the pendulum, they are just examples of problems that you can model using differential equations. These differential equations are already quite complicated. Let me go to the next slide because I'm getting kind of bored with the music. So you can model many things using differential equations. And one more example is bacterial growth. And this is probably the easiest or differential equation that we can derive. So as you know, if you have bacteria at some moment in time, then they're going to split after a certain period. And if you start with 2, then you have 4, and after the same period you will have 8, and if you wait again for the same period you will have 16. So you get something like this. This is a video that I found on YouTube.
Reproduce very simply and rapidly by doubling their contents and splitting in 2. Just one bacterium, dividing every 20 minutes, could produce nearly 5,000 billion bacteria in one day.
So you see that you have very fast growth here. In fact, we will see that we have exponential growth here. Now, let's see if we can describe this mathematically. So I'm going to try and describe this, and for that reason I'm going to call y of t the number of bacteria we have, number of bacteria at time t. So you see that often in calculus we work with functions f of x. If we talk about differential equations, they usually describe time-dependent processes, and then we use t instead of x, and we often write y for the function, but you could also have chosen f of x here. Now, if we want to know how many bacteria we have at time t, so at a certain moment in time, say time 0, y0, I know the number of bacteria that is given because I count them on a Petri dish or whatever. And then I would like to know how the population size develops in time. Well, the growth of the population so the rate of change, because every bacteria that I have at a certain moment in time is going to split, well, this growth of the population is proportional to the current size. So is proportional to the current size. So the way we can write that mathematically is the growth of the population, that is going to be y prime of t, that is the rate of change of the population size. And apparently that is proportional to the current size, and the current size is y of t. So what does that mean? Is proportional? It means that if y of t is twice as much, then y prime of t is also going to be twice as much. So in general, it means that y prime of t is some constant times y of t. So that is what this notation here is proportional to. It means that there is a constant in between them. And what we have found now, so this here in the highlighted area, this is called a differential equation. Differential equation. So it is an equation for an unknown function. I'm trying to find the function y of t, and I have an equation for it in terms of its derivative. And that is a differential equation. And then, since I'm naming things, the constant, we also give that a name here for the application. It is called the growth constant. Growth constant. So it's a fixed number. So what we have, we can actually solve this differential equation. So let us try to do that. We have dy dt, so that is the same as y prime of t, but I would like to write it like this, is k times y. And here I'm suppressing the notation that y depends on t, and why I do that will become clear in a sec. So I can rewrite this, and I can rewrite it to dy is k times y times dt, or if you like, I could also say that 1 over y dy equals k times dt. So that's just rewriting the differential equation. Now let me go to a new page. I'll copy the equation that we are currently working with. So here's a new page, and we have 1 over y dy equals k dt. Now what I'm going to do now is I am going to integrate both sides of this equation. So integrate both sides of the equation. So I just put an integration sign there. 1 over y dy is the integral k dt. And now we're back into the previous topic about integration, and these are not very difficult, right? Because the integral on the left, well, 1 over y, I know an antiderivative there. That's the ln of the absolute value of y equals k times t. And in principle, I would have to write integration constants there. So if I would be very precise, I would write plus c1 and plus c2 integration constants. Now note that I have two arbitrary constants. So instead what I'm going to do is I'm going to say, well, apparently ln y equals k times t plus c. And this constant c is then c2 minus c1. I'm just interested that there is a constant there, and I don't know about the size or whatever, so I just write it like this. Now, I'm going to assume that y is bigger than 0. So my population size is a positive number. That makes sense, right? Then I can forget about the absolute values here in the logarithm. So what we have is ln y equals kt plus c. So k we know, right? K, that depends on bacteria that we're working with, but it's some constant. And c is the integration constant. Now, I'm interested to find y. So what I'm going to do is use, well, the inverse of the logarithm, which is the exponential function. So I know now that y is apparently e to the power kt plus c. Now, if I have e to the power something plus something, I can split them. So let's write this as a to the power kt times e to the power c. And now c is an integration constant, so e to the power c is also a constant. So I'm going to say, well, that is a times e to the power kt. This a is e to the power c. It is just a constant, so I'm not interested that it was e to the power c before. A is a new constant. So what I have found, let's put that on the next slide. So the conclusion so far, at this moment in time, is that conclusion, we have found that the population yt is some constant a e to the power k times t. So indeed, as I already said, we have exponential growth. Now, as an example, let's say that we have we have the following data. So I'm going to try and translate this to an actual situation that you could have in a laboratory. So say that the bacteria population at time 0, so at some moment in time you start your experiment, you have this Petri dish with bacteria and you see that there are 100 of them. Bacteria population at time 0 is 100. Then after 60 minutes or after an hour, 60 minutes, let's say that it is 450. Now, you could ask yourself the question now, can we determine the population size at any moment in time? So let's call that y of t. Let yt be the population size at time t. So what we immediately know now from the data that has been given is that y0 equals 100, and if we work in minutes, then y60 is 450. And apparently that should be sufficient data with the formula that we have derived to determine capital A. So what we have, and actually we can also compute K now. So let's see what we have. We know that yt is A times e to the power k times t. So y0, if I use this formula, equals A. And I also know that it equals 100. So apparently our constant A equals 100. So yt equals 100 times e to the power kt. Now, because I have an additional data point, I've also given that y60 equals 450. That gives us a way to determine the growth constant, the k that determines how fast the population will grow. So let's see. So because y60 equals 450, we find, so on the one hand I have now this formula at the bottom here, 100 times e to the power k times t, and I also have this data point. So what I find is that 100 e to the power 60 times k equals 450. Now luckily we know everything about logarithms and exponential functions, so it's easy to find k now, because what we find is that e to the power 60k is 4.5. I've divided by 100 on both sides of the equation. I take the ln, and then we find that 60k equals the ln of 4.5. So apparently k equals ln 4.5 over 60. And if you would check on a calculator, you would find that that is approximately 0.0251. So the conclusion is, yt equals 100 e to the power kt with k equal to what it says above here, ln 4.5 over 60. So now I can compute the population size at any moment in time. This formula holds for t equal to 0 and every positive value of t that you can think of. Now there is one more interesting thing about this example, and then I move on to the next one. And that is that biologists are interested in the doubling time. So if you have a certain population size, so at time 0 I have 100, how long does it take for this population size to become 200? So let's see. So the doubling time. So for which value of t do I find that y of t equals 200? Let's call that t star. Let's say y of t star, and that's then the doubling time, equals 200. So what I have is that 100 e k t star equals 200, like this. So this is similar as what we had before. We have e to the power k t star equals 2. I can take ln's, and then I find kt star is the ln of 2, and then I can divide by k, and I find that t star equals ln 2 over k. And if you would compute that for the k value that we found, then we would see that this is approximately 28 minutes. So what that means is that if we start with 100 bacteria, as we have here, and we go to 200, that this takes approximately 28 minutes. But then also to go to 400, that also takes 28 minutes. And it takes the same period to get to 800 and to 1600 and so on. So after every 28 minutes, the size of the population doubles. Okay, so far for the bacteria. So let's see what we have found here. In general, we have seen that if you call yt the number of bacteria at time t, then we have the differential equation that's in the box here. So the first derivative, or the derivative of y with respect to time, is k times y. So that concludes the example of the bacteria. There is another one that I want to point out here, which is Newton's law of cooling. So what Newton's law of cooling says is that if you have a hot liquid, say coffee here, and if you would like to describe how it cools down, so you get your coffee and let's say that it's 80 degrees Celsius, then you put it in a room where it's say 20 degrees Celsius, then you know, just from experience, that it's going to cool down. And if you wait sufficiently long, then the coffee temperature is going to be 20 degrees Celsius if you have a large room, like a lecture room. Now, the idea that Newton had to describe it is that how fast the temperature will go down depends on the temperature difference. So you could imagine that if you would put your coffee into an environment where it's also 80 degrees Celsius, it doesn't cool down, it just stays 80 degrees. But if you put it in a room where it's like 60 degrees Celsius, it's going to cool down slower than if you put it in a room where it's 20 degrees Celsius. So the way you can describe this is as follows. So again, I'm going to derive a differential equation, and now I'm going to call y of t. So y of t is going to be the coffee temperature. Y t coffee temperature at time t. I'm going to assume that when I pour the coffee, so y0 is 80 degrees Celsius. And I'm going to assume that the room temperature is 20 degrees Celsius. So the idea here that Newton had to describe this, let me put that on the next slide. is that the rate of cooling, let me first write it down in words. So the rate of cooling, so the change of the temperature in time, is proportional to the temperature difference. So the temperature difference of the coffee temperature and the room temperature. Sometimes that's called the ambient temperature, the surrounding temperature. So in the formula, the rate of cooling is y prime of t is proportional to, we write that with this symbol, y t minus 20. So I'm going to assume that the coffee temperature y of t is bigger than 20 and then y t minus 20 is positive. So what that means is that y prime t is some constant times y t minus 20. So you see that this is a little bit like the bacterial growth. For the bacterial growth we only had this part here, but now there is this extra minus 20 here. So it's a little bit more complicated, but it turns out that we can still solve this. So this differential equation, this is again the differential equation. I can solve it using a technique that's very similar as for bacterial growth. So I get dy dt is k times y minus 20. So I can rewrite this as 1 over y minus 20 dy equals k dt. And again, I'm going to integrate on both sides of the equation, just as I did in the previous example. And again, this first integral, we have to look for an antiderivative. That's going to be the logarithm, right? It's going to be the ln of the absolute value of y minus 20. And this is going to be k times t. So let's write that down. So what we get here is that the ln of y minus 20 absolute value equals k times t plus some integration constant. I'm going to assume that y is bigger than 20. So then I find that y minus 20 is e to the power kt plus c. As before, that's a to the power kt times e to the power c, which is a new constant, e to the power k times t. So apparently what we find is that the coffee temperature, y of t, equals 20 plus a times e to the power kt. So this is the temperature development in time. For every moment in time we know the temperature, but there are still two constants in here, a and k. So if we use that y at time 0 equals 80, so the coffee temperature is 80 degrees Celsius at time 0. So what it tells us is that 80 equals 20 plus a e to the power 0. E to the power 0 equals 1. So we find that a equals 60. In other words, yt equals 20 plus 60 e to the power kt. And then we need additional data to find this k value here. So this k tells us how fast the temperature will go down, how fast the coffee temperature will go down, yeah, from 80 to 20. That's what we expect. So let's say that we measure the coffee temperature, temperature after 2 minutes. And let's say that we find that it's 27 degrees Celsius. So then I can use this to determine my K value, because then I find that Y2 is 72 on the one hand, and it's 20 plus 60 e to the power 2k on the other hand. And you see that we can now find what k is. So we find that 52 equals 60 e to the power 2k. In other words, e to the power 2k is 52 over 60, and k itself is 1/2 times the ln of 52 over 60. And if you compute this, then you find that this is minus 0.0716. So what we find, conclusion, the coffee temperature as a function of time is 20 plus 60 times e to the power minus 0.0716 times t. And before I move on, two observations. So here we take the ln of a number in between 0 and 1, which means that we find a negative k value. And that makes sense, because if you look here, this thing needs to go to 0. So I need a negative number times t. If t is going to infinity, then this thing is going to 0, and the coffee temperature is going to be 20 plus 0 is 20. And that's what we expect. We expect the coffee temperature to go to 20. And this apparently tells you how fast that is going to happen. So you should expect a negative k value here. That makes sense. So wrapping up this example, we find that if you let yt be the coffee temperature, that we find this differential equation, and we managed to actually solve this and to find an analytical solution for yt, for the coffee temperature. The two examples that I just presented and where we could actually solve the differential equations are examples of what are called separable differential equations. So we start with a differential equation that looks like, well, y prime of t is some given function. And then if you can move all the y's to the left-hand side of the equation and all the t's to the right-hand side of the equation, then it's called separable. So this is the original differential equation, and so for the bacterius we had k times y for this function f for the right-hand side, and for the coffee we had k times y minus 20, and that can be any function basically. What we then did is move everything with y to the left side of the equation like this, and everything with t to the right side of the equation, and then we integrated on both sides. Now, as you can imagine, you cannot always do that. So for instance, if this right-hand side here, this f function, if that would be the sine of t times y, then you cannot separate them. So we are studying a special class of differential equations where you can actually manage to do so. And even if you can move all the y's to one side, all the t's to another side of the equation, you still don't know whether you can find these antiderivatives, because integration doesn't always work. There are many functions that we cannot find an antiderivative for. So only special differential equations can actually be solved using pen and paper. Let's do an example where we have such a separable differential equation. So we have this function here. So what I can do is I can rewrite it. So y prime I write as dy dt. Then I multiply like this, and I find y squared dy is this polynomial in t dt. I integrate on both sides of the equation. So I find a y cubed if I do that. So y is the cubic root of this expression here. What you still see is that there is this integration constant. So if I find this integral, I have an integration constant c1. If I find this integral, I have an integration constant c2. I take them together, so capital C is c2 minus c1, and then this 3 is also 1/3 is also compensated for. But in principle, for different values of capital C, I find different curves. And here I have plotted these curves for different values of C. So here in the legend you see which C values I chosen. And every different C gives a different solution. So if you just look at a differential equation like we have here, you're not going to find one function, but you're going to find a family of solutions. Now, if you want to determine which of all these curves here, I've plotted 5, but there are infinitely many, which one you need, well, you can do that by, for instance, saying what t should be at time 0. As soon as you fix the temperature at time 0, for instance, you say, well, at time 0, I want it to be this value, it means you're on the green curve. If you fix the temperature at time 0 to be here, you're on the purple curve. So by fixing basically the state at time 0, you can choose one of the members of the family. So let's do that here. So let's say that we require y0 to be some value y0. So here it's y at time 0, and this is what we prescribe, the constant. And that is called an initial condition. Then we fix one of the members. So for our example, if I say that y at time 0 should be 3, then I find c equals 27, and I have one unique solution to the differential equation. So what that means is, if you just look at the differential equation, you're going to find a whole family of solutions. If you want to pick one of them, one member of the family, you should prescribe an initial condition. To finish this video on differential equations, I'm going to study one more example, which is on population growth, and it's a model that has been introduced by Verhulst. He was a Belgian mathematician, and in the 20th century he made a model for the growth of the Belgian population as a function of time. So the Belgian government wanted to know how many people are going to live in our country in 2, 4, 6 years' time. And what he studied is a model for population growth where, in principle, so the rate of change is proportional to y of t. So that's what you have seen for bacterial growth. But that in a country with people, you know that there are limited resources. There is only so much food, so many houses to live in, and so on. So what he introduced as an extra is that the population cannot simply keep growing. It cannot double all the time. That's not going to work. So we are going to assume that there is a maximum population size capital M that the environment can sustain, and it's called the carrying capacity. So this capital M tells us that if the population is at size capital M, then all food, all houses, all infrastructure is being used, but there shouldn't be more people. It's kind of the maximum population size that still is okay for the country to have. So what Verhulst did is that he said, well, on the one hand, the population size is proportional to, the rate of change is proportional to the current size. On the other hand, it is proportional to m minus y, which means that if the current population size is lower than capital M, this is positive and it can still grow. But as soon as it's going to be larger than capital M, then this is going to be negative and the population is going to decrease. So the full model that he introduced is this. The rate of change of the population is proportional to y times m minus y. And this is called the logistic growth model. So this is proportional to, which means that there is a constant k in between. So y prime of t is k times y times m minus y. So this is again more complicated. We start with bacterial growth with just k times y. Then we had something like the coffee temperature, where we had that k times y minus 20. And this is yet again more complicated. So we get that the rate of change is proportional to k times y times m minus y with m, the carrying capacity. Now what may be surprising here is that we can also solve this differential equation. So let me write it down on a new slide. So what we have is that dy dt, the change of the population size in time, equals k times y times m minus y. Now, as we have seen before, if you just look at the differential equation, it has many solutions. And there are two special solutions. So if you would start with y0 equals 0, then you see that dy dt equals 0. So it doesn't change, that's what it says, right? dy dt equals 0 means that y itself is constant. So then we have that y of t remains 0. And of course that makes sense. If you start with a 0 population size, it remains 0. But also, if you would start with y0 equals m, then you also see for y equals m that dy dt equals 0 and yt equals m. So that is also a solution of the differential equation. If you start at the carrying capacity, then the population doesn't change size. So those are special cases. Now let us assume y unequal 0, y unequal capital M. Then what we find is that, so I have this differential equation, and now I'm going to divide both sides of the equation by y times m minus y. And it's okay to do so since I've made this assumption. So there I do not divide by 0 then. So what I find is that 1 over y times m minus y dy equals k dt. So this is, apparently the differential equation was separable, and I've separated it like this. So if I now integrate, then the right side, we have seen that before, that's easy, because that becomes k times t plus some constant. The left side is a bit more involved, because we cannot readily integrate this. This is not a logarithm, because if I would multiply this, I would get a y squared. I would get m times y minus y squared, and if I have a y squared there, I don't know what to do. So I need a trick there. So in order to find this integral, what I need to do is the following. I want to, so this is like one fraction. I want to make two of them that are simpler. And what I'm going to do is I'm going to write the numerator as y plus m minus y. Now, if you look at the numerator, I wrote y and minus y, so they cancel there. So really what it says here is capital M, which is a constant. There was a 1 there, so I write 1 over m times what I have here. So this is a trick, and if you've seen that once, hopefully you can remember how to do that. Because what I now find is that this equals 1 over m, and then in between brackets, so this here is y divided by y times m minus y. So the y drops out, and I find 1 over m minus y. And the second term is m minus y divided by y times m minus y. So the m minus y drops out and I get a plus 1 over y. And the great thing is that each of these two I know how to integrate. So if I call this integral I for integral, then I now find that I is apparently the 1 over m. I can write that in front, times, and then I get the integral 1 over m minus y dy plus the integral 1 over y dy. So what I find, let us assume 0 less than y less than m, then I find I is 1 over m. The primitive for m minus y, the antiderivative, is the logarithm of m minus y. And I don't write the absolute value signs here because I'm going to assume here that this holds, so then I can forget about the absolute value signs here. There is one tricky bit here that you should remember, because there is a minus y here. If you differentiate, you get 1 over m minus y, but with the chain rule you would get an additional minus sign. So I have to put a minus sign here to compensate for that. And then here we get ln y. And now I have basically the ln of this thing minus the ln of this thing. And then I can take them together as one logarithm. So this is the same as 1 over m. And then I take the two logarithms together and I get y divided by m minus y. Okay, so we are good on our way to solve the differential equation, because what we have now found, if we put things together, is, let me go to a new page. So the integral for y we have just found is 1 over m times ln y m minus y. And that should equal what we previously found for t, k times t plus c. So I can multiply both sides of the equation with capital M. And then, no, let's do that first. ln y m minus y is k times m times t plus, well, c times m, I'm going to call that c tilde, because it's just a constant. I don't care about this extra m there. Now I take the exponential, so I find that y over m minus y equals e to the power k m t plus c tilde, which is e to the power k m t e to the power c tilde, which is a new constant. Let's call it a again, e to the power k m t. Okay. So not quite done yet, because I would like to find y, and I have now an expression for y over m minus y, but it's not so difficult to solve it from this, because what we have is that y is apparently a times m minus y times this exponential. So I have a m e k m t minus a y e k m t. I can move this one to the left side of the equation, and then what I have is that y plus a y e k m t equals a m e k m t. Here I can pull out the y, and then in between brackets I get 1 plus this exponential. Then I can divide by it, and then we're almost to the final form. So what I have now found is that apparently y equals a m e k m t divided by 1 plus a e k m t. So quite a bit of work. And I'm not completely happy here yet, because I have still this capital A in here, and this is just from the integration constant. And for our physical problems, or if you talk about people actually studying population dynamics, they don't care about integration constants. What they would like is to have a solution in terms of the population size at time 0. So let's try to do that. So let us now assume that y at time 0 equals, well, some given population size y0. So that's just a fixed number. That's the Belgian population at our starting time, and then we want to study how it's going to develop in time. So if I plug that in, then in this general solution, let's plug in t equals 0 and see what we find. So we find a times m times e to the power 0, that's 1, over 1 plus a, and that should equal y0, which means that a times m is y0 times 1 plus a, which is y0 plus a y0. So what I find, let's see, I'm trying to compute a here. So I have that a, m, and I'm going to move this one to the left side of the equation. So that's going to give me a minus y0 equals y0. So a is y0 over m minus y0. Okay. Almost there. So let's see what we have. So we have this expression for y, but that still involved capital A. And I would much rather have the solution in terms of things that actually make sense in practice for a population. So that is true here, because here we have the population at time 0, and we have this capital M, the carrying capacity, and they all have an interpretation. So putting these red formulas together, I'm going to plug in the A into that equation, and then we will be done. So let me do that. And I'm going to need a bit more space for that. So what we then find is that y equals, and there was an a here, so I replaced that with y0 divided by m minus y0 times m times the exponential. And in the denominator I had 1 plus, and here again a, so that's going to be another y0 m minus y0 times the exponential. And you see that I have an m minus y0 here and twice in the denominator. So let's multiply the whole fraction with m minus y0 divided by m minus y0. Then in the numerator, let's do that in red, this here and this here are going to cancel. So what I find is y0 times m times the exponential. And in the denominator, I have this 1 times m minus y0. So let's write that down. That's going to give an m minus y0. And for the second term, this thing and this thing are going to cancel out. So what is left of the second term is plus y0 e to the power kmt. So this is great. I'm perfectly happy with this. This is what I wanted to derive. Now I know that the population at any moment in time is given by this long formula. Back to the slides. So that is here. The result of our computation is this formula here. And if you would plot that, so I've chosen certain values, then what you see here, it's starting at some positive value for y0. So it looks like it's almost 0, but it is a positive value. So we have down here, we have y0 larger than 0. Then in the beginning here, you see that it's a bit like exponential growth. But then at a certain moment in time, and that is around here, you see there is an inflection point. So the growth is going to slow down. And for t going to infinity, apparently the solution is going to m. And you can also tell that from the equation, because here we have this equation. Now if you let t go to infinity, well, we know that the exponential is going to blow up. It's going to be a very large number. So I'm going to divide. I'm going to look at the denominator. That's the standard trick. I say this is the largest term in the denominator. So I'm going to divide everything by that. And then you see that I get the limit. T is going to infinity. In the numerator, I have my0 exponential kmt. And I divide that by the exponential. In the denominator, I have m minus y0 divided by the exponential plus y0 divided by the exponential, but that means it's gone there. So in the numerator, the exponential drops out. And I can now take the limit. And the limit is going to be, in the numerator, I'm left with my0. And in the denominator, I find 0 plus y0 equals m. So indeed, the model has the property that if you let t go to infinity, that the solution will go to capital M. Also, what you can tell from this solution is if you plug in t equals 0, then I find, let's write that down too. Let's write it in black, then you can separate it. So also, if you compute here y0, in the numerator we get my0 times 1. In the denominator we have m minus y0 plus y0 times 1. So what we get is my0 over m. In the denominator it says minus y0 plus y0. The capital M drops out and we have y0. As it should be, right? That's the way we constructed the solution, but it's always nice to check that. Also, during an exam, if you have a question with differential equations, check whether it solves the differential equation and whether it solves the initial condition. So what we have found here is that initially here we have almost exponential growth. Then the growth slows down, so that's this region here. And then for t going to infinity, there is a horizontal asymptote as the population goes to capital M. So quite a long video this time, but we have reached the end of it. So what we have seen is that many problems can be modeled using differential equations for a certain type of differential equation. So not everyone, but sometimes you can separate them. And you can separate them into moving everything with y to one side of the equation, everything with t to the other side, and then integrating both sides of the equation. And we have in particular studied the logistic growth model by Verhulst and found a solution there. So I hope this gave a nice introduction to the topic of differential equations, and I will see you in the next one.